Where the heck is Kim and Matt? Do we know? They weren't in all day?
No, nobody knows.
Everybody's so weak. Everybody's so weak. Okay. Question 1. Does anyone have a spare pen I could borrow? I lost it. Find it out. A pen or pencil, whatever. Yeah, thank you. Did you watch the videos that you missed or not yet? Yeah, the 2 that you missed, was it? Okay. I don't think you missed any classes recently for me, actually. And Andek, you didn't miss any classes recently for me. Okay. So you'll be alright with this tutorial because you saw it. Okay. You were here during this one. Okay. A radioactive sample initially has 10 to the 24 atoms and an activity of minus 10 to the 23 equals. What is the value of the decay constant? So what formula do I need here? Do you remember which formula it is? Anyone remember?
I have an answer, but I don't have a formula.
You don't remember which formula you used? I'll write it down.
A equals negative.
That's it. A equals negative lambda n. So the A is minus 10 to the 23. The lambda is what we want. And the n is 10 to the 24. So the minuses cancel. And the lambda is 0.1. And what's the unit for lambda? Oh, did you not write your unit down? Very bad physics student. Tut tut tut. I will take 1 mark away from you in the exam if you do that. What's the unit? Do you know?
Hertz.
Yeah, Hertz. Correct. Okay. B. What is the activity after 10 seconds? So what's the formula we need here? Activity after 10 seconds.
A equals
Yep.
minus 10 to the 23 e to the power.
Yeah, what was that formula that came from? A equals A0 E minus lambda t. That's what it was, Siva. So that would be minus 10 to the 23 E minus 0.1 times 10. Does anyone have that typed out?
Minus 3.7 times 10 to the power of 22 or so.
22? Probably 22. I would say that seems about right.
Yeah.
Great. And what's the n? Now, to do part C here, you actually have 2 ways you can do it. You can either use this formula, or you can use this formula. Which one did you use, Siva? You didn't get this one? Yeah. Andek, did you get this one? No. You can use both. They should both work, okay? Let's look at both. So this one here would be n equals n0 e minus lambda t. And this one here, n would be minus a over lambda, which would be plus 3.7 times 10 to the 22 over 0.1. So I think this is 3.7 times 10 to the 23 atoms. And I think this is also going to work out to be, they're both going to be this, I think. I don't have my calculator, but maybe you could check. Yeah? Oh, just atoms. Yeah, number of atoms. Yeah? It's okay. D. How long until n equals 10 to the 21? So we can use this formula again, n equals n0 e minus lambda t. N is 10 to the 21, and n0 was 10 to the 24, and we're looking this time for the t. So, usual story, we'll divide by 10 to the 24, and that gives us 10 to the minus 3, equals e minus 0.1 t. I think we all know what happens next. Log and log. So you'll get t will be log 10 power minus 3. So that's log 0.001 over minus 0.1. Now what's that going to be?
69.1.
What is it?
69.1.
69.1 seconds. Okay. You have that? Yeah? Can we go on to number 2? Now for number 2 you need your periodic table. Do you have, does anyone have it with them today? You have yours? Yeah? Yeah. So you have sodium 24. How many protons are in sodium? Sodium is Na, isn't it? Yeah, how many protons are in sodium? 11. So that's the sodium. And you're told it decays by releasing a beta particle, beta radiation. So it becomes something plus E minus 1, 0. So this must be 24. And this guy has to be 12 then. What has 12? Carbon? No, not carbon. Magnesium. Right, so that's the answer for part A. The answer is, what will the atom become after the release of the beta particle? It will become magnesium. Is that okay? Andek, is that okay? Are you sure?
Yeah.
Yeah. Continue. So the next part, I give you the formula n equals n0 e minus lambda t. Now, n is the number of atoms. Yeah? Now, what do I say? I think I told you something wrong in part B, perhaps. I said multiply by the molar mass and divide by Avogadro's number. I think I had that exactly backwards. It should be the other way around. What I'll do here, no, actually, I think I'm right. So first I'll divide by, first I'll divide by Avogadro's number. You know, the 6 point whatever times 10 to the 23. We'll call Avogadro's number Na. So, if n represents the number of atoms, not atoms, I should really say, isotopes, and Na is the number, is Avogadro's number, what would this represent, n over Na? The number of particles divided by Avogadro's number. Moles. What letter do we use for moles? Yeah, but what type of n? Small n, yeah. So this means the number of moles equals the number of moles at the beginning, E minus lambda t. Okay, now I'll multiply by molar mass. What letter do you use in Lorraine's class for molar mass? Just n by itself? A big N. like this. Yeah? Okay, so what is n times the molar mass? The number of moles times the molar mass, what's that? What is it, yeah? M or, yeah, what's that? Yeah, in other words, just the mass. So what I'm trying to show you in this question is you can make this formula that the mass is equal to the mass at the beginning times E minus lambda t. So if you have time here and you have mass in grams, it too exponentially decreases. That's the point with that question. Okay, so that's a little proof that might be useful for you to know. So I think you should write this down. Yeah? Is it okay? It's okay? Yeah, continue? Yeah? Okay. C. What is the lambda? So if I use this new formula, we know that after 7 hours there's 5 grams, but we started with 10 grams. Now, okay, 10 grams, sorry, 5 grams equals 10 grams E minus lambda. Now we should change our time into seconds, okay? But we can keep it as hours as long as we remember all our time is in hours now. That's okay. So I'm going to use 7 hours and let's see what we get for lambda. So if I divide, I get 0.5 equals E minus 7 lambda. You know the story. Log, log, cancel, cancel. So you get lambda is log 0.5 over minus 7, which equals. Zero point zero nine nine. 0.09999. Okay, yeah. What's the unit? Because remember, hertz is per second. So the answer is 0.099 per hour, not per second, not hertz. Now, if you don't like that, you know what to do. Instead of using 7, you use 7 times 3,600, if you didn't like that. But is it okay that I used hours, or would you have preferred me just to have stuck with seconds? Like, do you get how it's a little bit different? Yeah? Okay, D. How long until you have 10%? Right, if you start off with 10 grams, how much would be 10%? What would it be? Yeah? 1 gram. So my question really is, when do I have 1 gram? So all I have to do is solve this, and then I have my answer. Right, so that works out to be 0.1 equals E minus, you really know what to do now. What happens next? Log and log, cancel, cancel, and we have our T. Whoops. Log 0.1 over minus 0.099. which is
23.3.
what unit? Yeah. Because of we're using hours for this here. Now, can we go on to number 3? Yeah? Chow, number 3? Okay. Number 3 is interesting because it explains some, I wouldn't call it a problem, but it, what would you call it? It's something students wonder about. Okay? So, if you were to look at your graph for n equals n0 e minus lambda t, this graph is exponential. Does it ever reach the x-axis? No. But in real life, it does reach the x-axis. So this is an example of when you use something to describe a physics idea, but the formula is more perfect than what happens in real life, if that makes sense. Do you know what I mean? Like, the formula is really, really accurate, but it doesn't perfectly represent what's happening in real life. Because in real life, what really is happening is the graph looks more like this. It's like steps, okay? And I can show you why. So let's imagine we have 100 isotopes of uranium-238. After some time, we'll have 50. I can't, what did we say the half-life of uranium was? I don't remember. Anyways, after some time again, we'll have 25. You know, and we're looking at the graph, and the graph goes smoothly like this, we think. But after some time, we don't have 12.5. Right? Because you can't have 12 and a half isotopes. You can either have 12 or 13. So what happens is 50% of the time it'll become 12 and 50% of the time it'll become 13. Then after that you'll have 6, but if it was 13 then it will sometimes be 6 and sometimes be 7. So we picture the graph as being smooth, but really it's more like this. It's kind of a little bit rough. Yeah? So if we start off with 100 and then we get down to 0.5, then really that means we probably have 0 or we probably have 1 left. Because you can't have 0.5 of an isotope, right? So as soon as we have less than half an isotope, then we probably have no isotopes left. So my question here is to figure out when n would be roughly half an atom, half an isotope. Roughly when it's half. What information do I give you? I tell you at how many do we have? We have 1 milligram. We have 0.0. No, I'm not going to try and do it in my head. We have 10 to the minus 7 kilograms of lithium-8. The molar mass of lithium-8 is 13.882 grams per mole. Right, so my first thing I want to work out is how many lithium isotopes do I have? So we know the story here. Oh, I should actually be using grams and not kilograms, because it's molar. Right, 10 to the minus 3 grams, 13.882 grams per mole. So 10 to the minus 3 divided by 13.882, that's how many I have, multiplied by Avogadro's number. So could you type in, please, 10 to the minus 3 divided by 13.882, and then take your answer and multiply it by Avogadro's number. 6.02 times 10 to the 23.
4.34
Yeah.
times 10 to the 19.
Isotopes of lithium. We want to know, that's how much we have at the beginning. We want to know when will we have only half an isotope. Because then that means we probably have no isotopes. So we have to solve this formula. 0.5 equals 4.34 times 10 to the 19 E minus lambda, which I give you in the question, T. It's at the end, 0.825. Yeah? Right, so we all know what's going to happen. We first divide, then we take the log. So divide. Then we take the log. And then we divide by this. And now we have our time in seconds. Only 55.6 seconds. Okay. So what we say is, after we wait 55.6 seconds, we no longer expect to see any radioactive lithium 8, wasn't it? Lithium 8 isotopes. So basically what I'm saying here is, if you wait 1 minute for this, if you wait 1 minute, then 1 milligram of lithium 8 should fully decay away and you have no lithium 8 left. But mathematically that's not what you have on the graph. If you were to graph this, after 1 minute, you still are supposed to have like a tiny amount of lithium. It's just the problem is that this amount would be less than 1 isotope. Which of course you can't have. So really what happens is the graph goes like this, goes chunk 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 bunk, and hits the floor. Yeah? Okay. I thought that was an interesting one to do, because sometimes students ask me, but the graph never reaches the x-axis, so that means it's always radioactive. Well no, it does reach it, technically. Okay, that's the radioactive decay equation. Let's go on to half-life now. Oh, sorry, you need a minute, Andak? Yeah, no problem.
Right now.
Mm-hmm. Yeah. Okay. Half-life now. Such a nice sunny day, and here we are studying physics.